Okay. Today we're talking about disjoint sets, and there's a homework 3 that's due tonight, and there's a programming assignment that's due, well, at the end of November, but I encourage you to look at it now. And as a warm-up, I would like you to tell me how many up trees are represented by this parent array. Remember, parent array representations are telling you for a particular node who is the parent of that node. So this is I want the parent of node 3. I look in there and it says the parent of node 3 is node 3. So anyway, the question is how many up trees are represented by this particular array? And I will give you, I don't know, how long do you want? A minute? A minute. And if you finish that, then you can go on and figure out what's the maximum height tree in this collection of trees, collection of up trees. Oh, you want a midterm 2 solution party? Yeah. Okay, I'll ask.
And a PA2 would be awesome too.
PA2. Okay, I'll ask. I have a meeting in minutes, so I'll ask in minutes. Okay, so why did I only give you a minute to solve this question? That seems cruel. How do you figure out how many trees there are in a parent array representation quickly? Lots of people, yeah. Yeah.
How many representations?
But how would you do it quickly? I mean, really quickly. Like looking at this array, can you tell how many there are just by looking at it quickly? Or do you have to construct all these trees? Yeah. The ones that are the roots, presumably if this is really a set of trees, the ones that are the roots of the trees are the ones that are pointing to themselves. They have themselves as a parent. And so you just have to look through this thing and say, oh, well, gee, there's only 3 of those. So there's 3 trees. So this answer should take you a minute. It actually takes you longer to answer the maximum height question because that you have to find long chains. And in order to find long chains, I don't know how to do that other than to sort of trace out the chains and see if you can find them. But did somebody have enough time to trace out the chains and figure out what the longest chain is? Yeah. 10 to 6 to 4 to 3. 10 to 6, that's right, to 4, and 4 goes to 3, and 3 goes to itself. So Do you remember these things now? I mean, let's fill out the rest of this tree. There's something else that points to 4, which is 0. So we've done 0, 3, 4, 6, and 10. What other? Maybe we should look at the tree that is rooted at 8. What things point to 8? 5. Okay. 5. Anything else points to 8? 1 points to 8. Anything else points to things that are inside of... We should really knock these things off. We've done 1, we've done 0, we've done 5, we've done 8, we've done 3, we've done 4, we've done 6, we've done 10, we've done... That's everything. Okay, so what else is left? 7 points to 1. Now what? Well, 8 is a root. Everybody remember this now? One more little tree to go. What's the root of the last tree? 11 points to 2. Where's 2 point to? The 9, oh, 9 is the root. Okay, great. 9 with 2 and then 11. So that's 11 and 9 and 2. Great. And then the height is 3. Because the longest path is exactly what you said, 10 to 64, 3. Yeah?
Is there a rule that it has to be a binary tree, or can we have...
Absolutely not. There is absolutely no rule that it has to be binary. Yep.
So like these would be 3 different like disjoint sets, right?
That's right.
And then like given like the disjoint set, we can't like tell the tree that it needs a parent array, so like tell the structures.
We need some sort of information, like either the parent array or pointers, or whatever you'd like.
Right. The order doesn't matter.
This is true. So these trees, they don't necessarily need to be ordered. I mean, an ordered tree is one in which the left child, if there are multiple children, there's an order to the children. That's what an ordered tree is. So these trees, there's really no notion of order for them. They're unordered trees. But they are rooted. They have a root. And so everybody points to the root in these up trees. They're the ones that go up. Is everybody at least... So we're going to use these types of trees, this kind of parent array representation and maybe other auxiliary arrays to perform the operations on disjoint sets that we want, which is union and find, in order to build up sets from singleton elements and build those sets up they're always disjoint. They never are overlapping. So we never have split this node between two things. It belongs to one set. Yep.
Also, just to summarize, so the array index represents a particular node, and the array element and the corresponding array element refers to the parent.
That's right. That's parent array. Yeah. Can 6 and 4 change? 6 and 0? Sure. You can switch. This is why this is an unordered tree. The children of the nodes that I'm writing here could be children in any order that you like. And it doesn't have to be a binary tree. There can be many, many children per node. In fact, that's what makes these things short, is that we can make them have many, many children. And we'll see how we do that in just a bit. Okay. So this is a slide from last time. We already talked about the runtime of find depends on the depth of the node k that you're looking for. That's the number of pointers that you have to follow to find the root, which is the representative of the set. And you should think of this as being, you might want to find the set for one element and find the set for another element so that you can check to see if they're the same in the same set. That's how you would perform, are these two things in the same set? And but then there's another operation, the union operation, that you would take two roots of two trees or take two elements, and union their sets together. So two sets become one set. Now, I've written this, and I feel a little guilty about this, so I'm going to tell you. I've written this as if the inputs were roots. What if they're not? What if I give you two keys, just K1 and K2, and I want you to union the two sets that contain, one set contains K1 and the one set that contains K2, I want you to union those two together. How would you do that? Yeah?
Could you go through each key and check its pairing and then see if they both, like, whether they are in the same set already or not? And then if they aren't, then you unionize it.
Do I go to the parents of these, or where do I go?
You go to its parents.
To the parents?
If it is not the parent, you go to its parents node and then its parents node until it loops.
Until it's a root.
Yeah.
Okay, great. So what is that called? That operation is called something, which is written on this slide. Find. Find. So what you do if you don't have the root of the tree and you're just given the key to get the root, you perform find. So you could think of this as being, you could think of it, you can think of this as being the output of find of key K1 and this one being the output of the result of a find of K2. And then you have the roots if you were just given keys. Okay, so all right, so now comes the test part. Here we go. If you are unioning two sets together, they are two sets are represented by uptrees. Remember, a set is all of the items in one uptree. And this is a forest of uptrees. So there's, in this case, 4 sets. So I'm giving you the roots of 2 of these sets, and I'm asking you to union them together. And what is the smart way to union them together? If I have, let's say, this one, well, let me ask it this way. Do I want to make this be the taller or this be the taller? So do I want the taller root to be this one or this one? We're going to choose one of those two. One of them is better than the other. How many people will vote for A? How many people will vote for B? How many people think A, parent of the taller, should become set to the root of the other? How many people think it should be B, that the parent of the smaller should point to the root of the taller? Okay. This is good. Some people are voting twice. That's okay. I don't mind that. But I want to make sure that everybody understands what the question is. I'm asking, there's 2 possibilities. What we're doing is we're setting the parent of one root to be the other root. So that instead of like, for example, instead of this arrow being here, I point it this way. That would be setting the root of the parent of the taller to have the root of the shorter be its parent. So that would be doing this, the parent of the taller. Alternatively, I could do this way. Maybe I should do it in different colors, but I'm not going to. I could kill this thing and I could point it this way. That would be pointing the parent of the shorter to the parent of the taller. So which one of these 2 should be taller? Now it's more clear, maybe. B or A? B. Well, you want to make the short tree point to the tall one, because what happens to the short tree when you make it point to the taller one? What happens when I have a short tree and a tall tree, and I make the short tree point to the tall tree? its height increases. So the depth actually of all of the nodes in this tree increased by 1. Now they used to be depth whatever, and now they're depth 1 more than that. So we're increasing the depth of the tree that's shorter. Somehow we're trying to keep the maximum depth small when we do union by, this is called union by height. So there's union by height and there's union by size. Those are your two options. And in both cases, if you use either one, then you get a property which you have to fill in the blank on. So you have to tell me what the height of this tree is down here. But before we do that, let me just show you how this thing works, and we'll do it with a little bit more complicated example. So there's another 2, node 2, and node 7 are on this tree. So now there's a tree of height 2, and then there's a tree of height 3, and according to union by height, which pointer do I choose to change? Node 0s or node 3s? Zero. I change the short tree to point to the higher one. The new root is the root of the tallest of the two trees. Yeah.
Is it because by unioning the two trees this way, we don't increase the height of the taller tree?
That is true. We do not increase the height of the taller tree.
This way.
Yes.
So how do we figure out the heights of your parents? You calculate it as we find.
How would you keep it? How would you keep the heights? What would you do? Well, first of all, let me ask you: whose height do you need? The parents or the root?
The root.
Okay, I need the height of the root. So what do I do? In this particular thing, when we're doing union by height, the only things that are changing are the heights of the potentially the heights of the root change. But when do they change? So, like, when would it be possible for the height of a root node to change? So I have, here's a root node, here's another root node. Presumably fines don't change the height of the tree because they're just fines. So unions are the things that change the height. So when is it the case that the height of one of these nodes is going to change? Yeah, when the heights are the same. So if this one, so let's say this is x and this is y. If the height of x is equal to the height of y, then when I do this, I don't have a choice. I could choose either one to be the short tree or the tall tree. It doesn't matter which one. But when I do this operation, the height of one of them, in this case it's y, goes up by 1. So it's going to change, but it's only going to change on unions, and I only have to perform one operation to perform the change. And it really, I can just keep an array of heights for all of these things also. Yeah. Yeah.
I was wondering, what is every union by 5?
Ooh, what is union by size? What do you think? Union by height.
Oh, total, yeah. Like, the sum of all of it?
That's what it's minimizing, but what do you think size is? Yeah, the number of nodes. So if I have a really, really big tree, lots of nodes in it, zillions of nodes over here, and I have a smaller tree with fewer nodes, then what I will do is I will root the resulting union tree at the big tree. So the small tree becomes a child of the big tree's root.
Regardless of height?
Regardless of height. Totally. Just the number of nodes. Why? Because it works. Just the same as height.
But,
Just exactly the same.
well, we want to minimize depth, right? Because that'll make flying faster.
Yeah, we want to minimize depth because we want to make flying faster. So the question here is, I'm sorry, we haven't even. I forgot that we asked this question. The question is, what's in the blue blank? If I use one of these schemes, then I have a set of up trees in my forest of up trees, and the claim is that an up tree in that forest, which has n nodes in it, has height at most what? There's an at most here. Less than or equal to what? This question is a really good question for you to think about. Because you know how to do this. No, I mean, you know how to analyze this. Because we've done it twice. It just doesn't look like this. It's a little bit different. But maybe the height one is easier than the size one, because maybe size is slightly more confusing, but you know how to do this tree stuff by height. We're trying to get a bound on height. And do you remember how we did that before? When did we do this before? First of all, do you remember? AVL trees. And when we wanted to bound the height for AVL trees, what did we do? How did we do that? Well, rotate was something that allowed you to balance an AVL tree. But if I gave you an AVL tree and I asked you, here's an AVL tree with n nodes, you're supposed to say, well, the height is no more than log n, something like that. But how do you remember how we proved that, how we showed that? It's kind of a weird kind of flippy thing that we did. It's kind of like instead of looking at the height, we looked at the we looked at the number of nodes. We had this recurrence relation for the number of nodes on a tree of height h. We said that the minimum number of nodes, the fewest number of nodes that you could have in an AVL tree of height h was something weird, 2 to the h or something like that. Same thing works here. What's the minimum number of nodes that you need in order to have an up tree of height h? I think this is one of those crowd participation things. This is one of those discuss with your neighbor things. You really, really should know this. And so I'm hoping that if you talk with your neighbor and try to figure it out together, you'll recall how this works. So maybe I'll give you maybe 3-4 minutes to try to do this. I think this is an important thing to learn. And if you have questions and you want to ask me, raise your hand and I'll come and talk to you if you are that have no idea what I'm talking about. Maybe you do. But in any case, let me just point out that you cannot make a long, skinny tree using the union by height rule. Right? You cannot make a chain of singleton children using union by height. Because if I take a node and another node, and I union them together, I get a chain of length 2. But if I take that chain of length 2 and I union in another node, it doesn't become a chain of length 3. This one is height 0. This one is height 1. So the height 0 guy points to the root of the height 1 guy, and I create a little tree that looks like a triangle, right? It's got 3 nodes with 1 root and 2 children. So you can't create a long, skinny chain of nodes following this rule. And all I'm asking is there a way for you to remember how to analyze this process of unioning by height so that you can see what the upper bound on the height is? Or, as you pointed out, the other way to look at this is to, say, fix the height and say what's the fewest number of nodes that you could have in a tree that has that much height. That's the same question, it's just the reverse. It's like looking at the inequality the other way around.
But n is the amount of nodes after you union two together.
N is the number of nodes that are in the tree. Yeah, and the thing that you know is that that tree was produced by performing union by height. Yeah.
When you're building the tree by doing union by height, are you just unioning like your existing tree and then one more node, or could there be like another tree that you build over here?
Yeah, it could be another tree, it could be anything. It could be a single node, it could be whatever should happen. But remember, when you're thinking about this in terms of analyzing it, you're thinking about it in terms of what's the fewest number of nodes, for example, that you can have in a tree that has height h. And so you imagine somebody has done union by height, and they produced a tree of height h, and you say, this tree of height h could not possibly have this many nodes. It has to have many more than this many nodes in it. It can't be made by a few number of nodes. So, for example, if you think to yourself, if I had a tree of height 3, maybe I could get away with having 4 nodes in that. No, because we know that it doesn't produce chains, and so the only way to get a tree of height 3 is to have more than 4 nodes. Yeah.
But how come I can't have a linear chain?
Try to do it. Try to make a linear chain. Try to use union to build one using union by height. I tell you, you're going to fail after a node 3. You can't create a chain of length 3. Of 3 nodes. Yes. Well, maybe everybody's done. Is everybody done with this exercise? Like, we don't want to exercise anymore. Try it. how many people are so apathetic and don't want to vote? A little bit more. Okay, let's stop thinking about it maybe. I'm sorry, I have to make sure that I'm actually on track for two, because I'm a little bit behind. Okay, so does anybody, I know one team got an answer, but is there anybody else that was successful, figured out what this number is, maybe? Why don't you say what your number is? Or function? Right.
In order to have type 0 responsible, type 1 requires 2 of them. For us to make type 0 and merge it to type 1, 2 type 1, which is 2 plus 2 is 4, and then include type 1.
Excellent solution. So I don't know if everybody heard that, but she's saying, look, when I'm trying to create a tree of height h, the only way I'm going to create a tree of height h with the fewest number of nodes, for example, is by having a tree that's of height h minus 1 and another tree of height h minus 1. And they get, when they're union together, one of them gets to be the parent of both. But that's how the thing is increased. We saw that's how height increases, is this way. When I have two trees of height the same. Those heights the same are height h minus 1. And so I will have, in order to create trees of height h minus 1, I have a recurrence relation. I have that the number of nodes needed to create a tree of height h has got to be greater than or equal to the number of nodes to create a tree of height h minus 1 times 2. I need 2 of them. And when I have 2 of them, then I perform a union. Then I can get a tree that has height h. And so the number of nodes in that union, this is a tree of height h minus 1. This is a tree of height h minus 1. When I union them together, I can get a tree of height h, and the number of nodes in that tree of height h is n of h minus 1 for the one tree, plus n of h minus 1 for the other tree. It's 2 times n of h minus 1. And the base case is, if I want a tree that has height 0, I need 1 node. And then you can look at this and you can figure out what it's going to be. It's going to tell you that the number of nodes in a tree of height h has got to be greater than or equal to something like I got a recurrence relation that says multiply by 2 every time. Somebody say something, please. 2 to the h. So now we know that the number of nodes in a tree of height h is at least 2 to the h, which means that if I have any tree of size n, then its height is less than log base 2 of n. Right? Because we know that this is true, n of h is greater than or equal to 2 to the h. And so any tree that has height h and has n nodes, that n is bigger than the smallest tree that has height h in terms of number of nodes, which is greater than or equal to 2 to the h. And then we just take log of both sides of that equation, and we get that its height is smaller than log base 2 of n. Okay. You can do the same proof for size. It's a little bit trickier, but it's not trickier. It's the same thing, really. You can do it. Okay, so great. So we do smart union. We get, so now we're at the point where we know find operations are only going to take log n time. Union operations, if I give you 2 keys, they're only going to take the time to find the root, and find the root, which is log n plus log n, and then perform the union, which is constant time. So I've got log n for union of arbitrary keys. I've got log n for find of arbitrary keys. What more do you want? It's great. Fantastic.
Also, since this tree isn't necessary like a binary tree or something like that. So how do we know that the fewest number of nodes is at least 2 to the h?
When is it the case that you can create a tree that has height higher than the current height of the tree? When can you do that? When does that happen? When you union. Union happens to be a binary operation. There's two things that are involved. It has to be the case that both of them are the same height in order for the height to increase. And so the minimum size tree that you can get, which has a particular height, is going to be a binary tree. It will be because the union operation is a binary operation.
Well, in this case, could we? Also, in this case, I guess we'll be undercount.
Maybe.
We have like a binary tree.
I'm pretty happy with log of n. I don't know about you, but I'm pretty happy. Yeah.
I still don't understand why you don't try to preserve that between 1 and find the relative constant.
Yeah. Why don't we just preserve the height to be 1?
Yeah.
Yeah. Well, how much time would it take to do a union?
We'd have to change all the pointers of this split.
Oh yeah, but what's that? That's easy.
Okay.
Well, maybe not so easy. But I think this is a great idea. I mean, I'm happy with the log base 2 of n, but the people that wrote about disjoint set structures were not happy about it. They came up with another scheme. So, this is the smart union code. You don't need to see this. They came up with a second thing, which is called path compression. So when you perform a find operation in a tree, you go all the way from the child, all the way back up to the parent, back up to the root, and that's where you find the representative for the set, all the way after all this work. Okay, but everybody that you visited along the way, that counts towards the running time of that operation. And what these brilliant people thought was that why don't we just short circuit all of those parents, all the chain of ancestors that we saw, and just short circuit them directly to the final outcome. So this is path compression. I perform find on 2. Here I am. I say, all right, 2 has a parent which is 4, which has a parent that is 1, which is a parent which is 5, which is a parent which is 3. All of these nodes along this chain, I am going to redirect to point to 3. So all of these, 5's already there. 1 gets directed there, 4 gets directed there, 2 gets directed there immediately. That's what path compression is. It compresses the path down to a height 1. How does it do that? It does it with this code right here. These 2 lines. Aren't they fantastic? When you perform, they're recursive, of course. When you perform a find, you have to perform recursively find on the parent in order to find what the root of the tree is. So it's like climbing up in the tree, this recursive call right here. And rather than just doing the recursive call, you reset the parent pointer for k to be whatever's found. And then you return whatever you've reset it to the person that called you. So essentially what's happening is you trace all the way up to the root, you find out what the root of the tree is, and then basically after you unravel the recursion on the way back, it resets all of the parent pointers to be pointing to the root. That's path compression. Does it make sense? Yeah.
Is there a way just to ensure how height 1 tree there's median?
Sure. You can ensure that it's height 1, but you have to do some work to do that. At every step you have to do some work in order to make sure that the trees are of height 1. So and the work that you're performing is proportional to the number of nodes in the tree. So your union operation would no longer be log n time. your union operation would be linear. It would take you n time to perform union, because if I union two sets of size n over 2, n over 2. So if you're willing to pay for union a linear time cost, you can have height 1 trees. But I'm not willing to do that. Yep.
Also, basically, resetting the pointer for all the nodes that we have visited, so that it points to like the
root.
highest axis.
The root. Yeah.
The root.
Yep.
So that may miss this, but why do we want to keep the uptree height 1?
Oh, we want it to be shallow.
Does that have to do with the ways for it? That's the thing.
No, it has to do with how long it takes to perform find. If I perform find, I have to chase the pointers back up to the root, and if the tree is really shallow, then the performance is just small. It's the height of the tree. That's right. So this is just a, one might say this is a heuristic. This is what we should do. It's a heuristic for restructuring the tree when you perform a find operation. You're going to pay a constant factor, so instead of find taking log n time, which is what we calculated before, it'll take 2 times log n time because it has to redirect the pointers, something like that. But who cares? It's just a constant factor. And in fact, what happens is it's an extremely effective heuristic. So a heuristic is something that you do that you can't really analyze. So this is not really a heuristic because we can analyze it. And let me just tell you what the outcome of the analysis is. This is the outcome of the analysis. So now the height is no longer log n for these trees that are using path compression and union by height or union by size. Instead, they have height log star of n. So if you perform, so the theorem that we're looking at here is saying if I perform m operations, either unions or finds, on a collection of sets that are n items, n things, then the time to perform those operations is m times log star n. You may not have seen log star n before. Maybe you have. I don't know. But anyway, this is the definition of log star n. Log star n is recursively defined. It's 0 if n is less than or equal to 1. And it's 1 plus log star of log n if n is bigger than that. You may remember the definition of log. Log of n is 0 if n is less than or equal to 1. And log of n is 1 plus log of what? If I would write log recursively, so log of n, it's equal to 0 if n is less than or equal to 1. And if n is bigger than 1, what is log of n? It's 1 plus log of n over 2. So contrast this log, which is very small. Log is like, tiny. Like log of 2 to the 65,536. Log of that number is 65,536. Log star is saying don't divide n by 2, but take log of n. So rather than dividing n by 2, you're taking log of n. So for example, log star of 2 to the 65,536. By the way, do you know what 65,536 is, so I don't have to keep saying this? Do you know what it is? 2 to the 16th. So this part right here is 2 to the 16th. So this is saying log star of this number is 1 plus log star of 2 to the 16th, which is equal to, well, the log star of 2 to the 16th is 1 plus, so this is now 2 plus log star of log of 2 to the 16th, which is 16. 16 is what? 2 to the 4th, which is 3 plus log star of What?
It'll be like 2 to the 2 to the 6.
This first number? Yeah, it's 2 to the 2 to the 16. Just the exponent is 2 to the 16. Yeah, that's why the parentheses are around the 2. This thing. That's the 2 to the 16.
But then when we do it, isn't it like log star? Oh, log. Okay,
Oh yeah, maybe there's an easier way to think about this. Okay, imagine that you took a number and you wrote it as 2 to the 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 1. Imagine you wrote it that way. Then log star would be the number of 2's in the tower. I don't know if that was helpful or not. But anyway, let's take a look. So log star, this would be log star of 4. 4 is 2 to the 2. So this is 4 plus log star of 2. 4 plus log star of 2 is 5 plus log star of 1. Log star of 1 is 0, so this is 5. So log star of 2 to the 65,536 is 5. The number of atoms in the universe is estimated to be 2 to the 273. So, if you have a database, which is a database for atoms in the universe, your sets representing atoms in the universe that are unioning together, then this would take less than 5 operations to perform the union operation, or the find operation, amortized over all of the M operations. Okay, so that's the running time that you get from doing path compression with the union by height. You get essentially M operations, each one takes pretty much constant time, about 5. So it is an increasing function. Log star n is an increasing function. Now, this was the original analysis for the disjoint set structure. Later analyses, if you're interested in this stuff, you should look at, there's a paper by Raymond Seidel and Mika Sharir. They showed, well, there were other people that showed this too, but they showed very nicely that it actually is m times the inverse Ackermann function, which is even more slowly growing than log star. So log star of 2 to the 65,536 is 5. The inverse Ackermann function of that thing is something like 4, maybe 3, 4. Anyway, it's really, really, really slowly growing. Isn't this cool? It's like not constant, but for all practical purposes, it's constant. Okay. Oh yeah. To tell you what's happening next time, we're going to talk about graphs. We're going to start talking about graphs. I do research on graphs. I do research on graph drawing, and this is another person who does research on graph drawing who drew a graph of graphs. If you zoom in, look at all the different graphs there are. And these are just the planar graphs. This is just graphs that you can draw without any edge crossings by drawing lines and dots. And she drew this great graph. Sadly, this great graph has edge crossings. I wanted to talk to her about this, but in any case, it's a lovely graph. You should take a look at it if you get a chance. It shows you how much diversity there is in this world of graphs. So anyway, we're going to talk about graphs next time. It's going to be great.